Hey, welcome back to another lesson in AP Calculus. We are in Unit 8. We are learning our last integration formulas today, and we are going to then look at some basic integration techniques. So in the previous unit, we derived the derivative formulas for inverse trigonometric functions. Not the I can't remember if it was the last unit or the unit before that, but in a previous unit. So I'm not going to go through the derivation of those derivative rules again. You can go back and find that if you want. The integration rule is simply the opposite. So this is just I'm just going to present you with the derivative rule on the left and the integration rule that goes with it. So we know we have 6 derivative rules: arcsine, arccosine, arctangent, cotangent, secant, cosecant. Remember that the derivative rules, when you take the derivative of a co, you have a negative. Basically, that's the only derivative difference between the derivative arcsine and arccosine. Now, since that's the only difference, we really only have one integration formula for each pair. So these pair here go to this formula here. The only difference is if you have a negative out in front of it. Okay, so we're just going to use arcsine, arctangent, and arcsecant. And you probably heard me say before that I just don't see the arcsecant formulas too often on the AB AP Calculus exam, but we're going to go through them anyway. These top two are by far the more common. There is, of course, this weird little absolute value again. Just like arcsecant had an absolute value in its derivative, we have an absolute value up here in the original. They are a little bit different than the derivative formula. So, arctangent, the antiderivative arctangent, you have to have a 1 over a in front of it. And that's, just going back to just kind of chain rule kind of stuff. And then here with the arcsecant, you have to have a 1 over a, but you also have to have an absolute value of u. Arcsine has u over a as well, the u over this a, but it doesn't have a 1 over a. So a little bit different there in the formulas. So just be aware of that. All right, now with the introduction of these last rules, we should consider a game plan we can use to conquer an integral. A lot of the Calculus 2 curriculum is called Techniques of Integration. And we do not go too far of that in AB calculus. So we just kind of knock on the door, but we don't kind of walk through it. We learn a few of them, but there's quite a bit more that can become more challenging. But there are still some that you can encounter. Most of the problems we'll encounter will be just basic U substitution, but it is possible that you would have a few other techniques that we need to use. So let's take a look at them. I've just kind of made a chart here for different techniques and an example problem. So we should be at this point fairly familiar with U substitution. Most integrals require some sort of fixing before you can take them. So U substitution, you can see my two examples on the right here. I would let U be x squared plus 3 here on this one. That would probably be best. On this one over here, we would probably want to let U be cosine of 2x. Now let's take a look at another technique. So division. We've seen a little bit of this. You've seen that when you have a monomial in the bottom, you want to go ahead and divide that into each one of these terms here. But when you have a binomial, it's a little different. You can't just divide that into each one so easily. But what we're going to do in this situation is we're going to use long division. And same with this. So the basic rule is going to be if ever you have a degree of the numerator equal to or greater than the degree of the denominator, we're going to use long division. And that will make it much easier to integrate. Now, if the numerator's degree is less, then no, we can't do that. In that case, maybe a U substitution will work. And our last one for now is completing the square. We're going to try completing the square whenever we have a degree in the denominator that is a degree in the numerator that is less than the denominator and you can't use a u substitution, but you might be able to make the denominator look like one of our arctrig functions that we just looked at. So you'll notice that on this example here, right here, we have a numerator that's a degree 0 and the denominator of degree 2. That's no, u substitution is not going to help me here because I would end up with an x still in my u. So that's a good example of when we would want to be using completing the square. So look forward to see how we do that. There are a few other things we're going to encounter. I don't list them here because I don't want it to be overkill, but occasionally you have to kind of massage out the kinks when using u substitution is a good way of thinking about it. We've already seen solving u for x. That's kind of massaging out the kinks. We saw in the integral of secant x, we had to multiply on top and bottom by something. You won't see that too often, though. That is a technique. And then finally, you can see that sometimes you have to do something really weird to fix the u substitution, kind of add or subtract things. So that's very rare to be on the AP exam, but I do want to expose it to you. I don't know if I've ever seen that question on there, but it's an important skill for an AP Calculus student to be exposed to. So we're going to look at all sorts of different techniques and different kind of challenging integral problems. So look forward to it as like a puzzle. And then we'll get started. Okay, so let's see what we got. On this one here, this looks a lot like the formula for our integration of arcsecant. So let's tell you what, let's grab that. All right. Wow, it's kind of ugly. I drew all over it, didn't I? Let me clean that up just a little. Let's grab this formula because we want to have it to look at while we're learning it. All right. So there it is. That is arcsecant. So we want to be real careful that we know what our a and our u are. So in this one here, this can be rewritten as dx over the square root of 2 squared minus x squared. So in this case, you can see that a must be 2 and u must be my u must be my x. Okay, so this formula works out perfectly, and I can even go further and say du is equal to dx. So this is exactly what we need. We know that this is the arcsine of my u, which is x, over my a, which is 2, and arcsine's the only one that doesn't require this 1 over a business, and then plus c. All right, so that's just a straight up application of the formula. Well, let's take a look at this next one. So you might think, oh, okay, I got this. This is easy, right? I can write this as the integral of dx over the square root of, just like I did before, 2 squared, and then 25x squared we'll just call 5x squared, and now we know what the u is and we know what the a is, but we need to be really careful here because the u is 5x. So don't just immediately think, okay, I've got it, u is 5x. I need to understand that if the u is 5x, then my du is 5dx. So I really need to do a u substitution here. So this becomes the integral, the dx becomes 1/5 du over the square root of 2 squared minus u squared. So this becomes 1/5 arcsine of u, which was 5x, over a, which is 2, plus c. So that u prime really needs to be 1 over u prime needs to be in front because of the chain rule. All right, our next one's a tangent. So let's grab the formula for tangent. Let me scroll up here and find it. I think it's not. I don't think it's too messy. I can just grab it right there. All right. So we have our tangent formula here. All right, so it doesn't matter. It's plus u squared or a squared. Doesn't matter. But the a is the thing without an x. That's what a is. That's the constant, and then the u is the thing with an x. So this is pretty straightforward. A is 3 because 3 squared is 9. U is x, so it works out just nicely. 1 over a is 1/3. Remember, only arcsine doesn't have that 1 over a business. Then arctangent u over a. So x over 3 plus c. All right, let's go on to the next one. Okay, well, how do we handle this one? Well, do you remember from our list of techniques that in this situation, this is where the numerator has a degree of 2 less than the denominator? I can't use u substitution. I could try it. I could try it. Let's look and see why it doesn't work. U would equal, let's say I'm thinking I'm going to do natural log here. Then I get du equals 2x dx. Well, actually 2x minus 4 dx, even worse. That just doesn't match anything. I can't, this whole thing on the bottom is going to be u, and then, I can't call 1 over 2x minus 4 in front of du. I can't do that. I can't mix x's with du's. So this just flat out does not work. So let's get rid of it. And instead, what we want to do is we want to make it look like this. So what I'm going to do is I'm going to group the first two terms together. And I'll use completing the square to make this a perfect square trinomial. So to complete the square, we take half of that number and square it. So half of 4 is 2, and 2 squared is 4. And we add it inside these parentheses. But if I'm going to add 4 there, I need to keep this balanced, so I also need to subtract 4. And so then this becomes, let me bring it over here, the integral of dx over this factors as x minus, and it should always be half of that number, half of this number, or the square root of this number. They really need to be the same. And it takes the sign in the front of the middle term, squared. And then 7 minus 4 is a plus 3. So now I can see that my a is the square root of 3. My u is x minus 2, which means my du is just dx. So I don't need to do any fixing of that. I can just apply the formula now. Remember, 1 over a on arctangent. So 1 over square root of 3. Then arctangent of u, which is x minus 2, over a, which is the square root of 3, plus c. All right, so let's do another one. All right, on this one here, we see the numerator is of the same degree of the denominator. And anytime the numerator is the same degree or more than the degree of the denominator, we want to do long division. So I'm going to long divide x plus 3 by x minus 2. I guess if you know a synthetic division technique, you could do that, but I'm just going to do long division. So we look at the first term in each one. X divided by x is 1, and then 1 times x minus 2 is x minus 2. But we have to subtract, so I distribute a negative and add, and I get 5. So this is equal to 1 plus the remainder over the divisor dx. The integral of 1 is just x. The integral of 5 over x minus 2 is 5 times the natural log of the absolute value of x minus 2 plus c. Now, you may be wondering why I didn't use a u substitution on x minus 2, and I certainly could. It would give me du equals dx, so this is just saying 5 over u du, which integrates to 5 times the absolute lateral log of the absolute value of u, and then I replace it. So anytime the derivative of what you're trying to think of as u is just dx, you don't really need to do u substitution, just keep it that way. So that's an example of having to divide. Let's try this next one. Okay, the numerator is greater than the denominator, so again, let's try long division. And I'll divide it by x plus 2. So x squared divided by x is x, and x times x plus 2 is x squared plus 2x. All right, and then we'll subtract. 3x minus 2x is x, and I bring down the minus 1. X plus 2 goes into x minus 1. X divided by x is positive 1. 1 times x is x. 1 times 2 is 2. But we need to distribute a negative. So I end up with a negative 3. So that tells me that this integral is equal to x plus 1, the quotient, plus the remainder, negative 3, over divisor x plus 2 dx. And again, this is pretty easy for me to integrate. This is x squared over 2 plus x minus 3 times the natural log of the absolute value of x plus 2 plus c. So just notice the similarity here, that when we had that 5 over x minus 2, it's just natural log of the absolute value of x minus 2. You're going to see that a lot, especially, I think, in our next unit. Okay, I have some practice problems for you to do. Make sure you're studying and using those new formulas that we got as we practice these different techniques. So pause the video before A, B, C, D, and I think that's it. So good luck. All right, let's see how you did. On this one here, you should have recognized that this is when we long divide. So I'll do x plus 5 divided by x minus 2. X goes into x one time, x minus 2, but I got to distribute a negative to subtract. And that gives me 7. So I rewrite this as 1 plus 7 over x minus 2 dx, which integrates simply as x plus 7 times the natural log of the absolute value of x minus 2 plus c. All right, let's try the next one. Okay, the numerator is greater in degree than the denominator, so you should have divided. X plus 3. Okay, x goes into x squared. X times x is x squared. X times 3 is plus 3x. And I'll distribute a negative. And I get x minus 2 when I bring down the minus 2. All right, and that goes into that one time. 1 times x is x, and x plus 3. And I subtract. And I get negative 5. So this is equal to the integral of x plus 1 minus 5 over x plus 3. That looks really similar. That's not the same problem we did earlier, is it? Oh, okay, no. All right. And all that is times dx, of course. We need that dx. And then when I integrate, I get x squared over 2 plus x minus 5 times the natural log of the absolute value of x plus 3 plus c. Okay. Let's try letter C. All right. This looks a lot like arctangent. So hopefully you realize that my A value is 2 and my U is 3x, because this is u squared. So du is 3dx. So 1/3 du equals dx. So 1/3 du over, all right, it's 2 squared for the a squared, plus u squared. So that becomes 1/3 times 1 over a times arctangent of u over a plus c. We'll just clean that up as I plug in u. U, remember, was 3x. And there we have it. Okay, let's try the next one. All right, this is your arcsecant formula, and I'm going to grab that for me right quick. So yeah, not one you see too often, but we want to just kind of make sure we're aware of it and, use it. I'll just use this one. Be able to use it if it comes up, all right? Just, right before you go into that AP exam, just go over these formulas. Make sure that you've got them in your head, locked in there. Okay, so we can see here that u would have to be 3x, and then du would be 3dx, so 1/3 du is equal to dx. So I'm going to rewrite this with 1/3 du replaces my dx. This here is u, 3x was u, and then the square root 9x squared is u squared. And then that's just minus 1 squared. So my a is 1, so 1 over 1 is just 1. We don't need that. So arc 1 over 1 times arcsecant, the absolute value of u over a. Again, a was just 1, so I don't really need to put that. So just 3x, and then plus c. All right. And I think that's all for this lesson. So I will see you in the next one.